Hello, and welcome to Spectral Clustering Part 8 of the series. My name is Che from Northeastern University. So far we've really concentrated on this following equation that essentially measures the, the relationship between two clusters, alpha relationship. Now, if the relationship is small, then it means that the two clusters are not similar to each other. But the relationship is large, it means that the clusters are similar. Now, if we look at these two clusters, obviously we want them to be as far apart as possible, so it's easier to tell them apart. If they start getting really close to each other, then if another cluster is like that, then it kind of becomes confusing. So our whole goal is to find a way such that we find some kind of clustering with F, such that the relationship between the two clusters are as far away from each other as possible. So to recap, now remember we have some kind of data X, right? And data X has multiple samples, sample 1, X2, X3. And each sample, such as X1 here, could be like a single dot of 3 and 4, which could be like a dot here. And 4 and 4 could be another dot here. So that's our data. And what we're trying to do is we're trying to solve this right here, which essentially says that we're trying to find the argument, F, that minimizes this whole expression. Okay? Now, if you remember what F and Fi and Fj is, when you have F1 is equal to 1, it's either 1 or 0. So if F1 is equal to 1, it means that X1 here, X1, belongs, is an element of a group, the cluster A. Now, if F1 is equal to 0, it means that X1 does not belong to the cluster A. So on and so forth, F2 equal to 1 or 0, that will tell us this. So by having a vector of like 1, 1, 1, 0, 0, 0, we'll say that, essentially say that the first three, X1, X2, X3, are all belong to the same group A, whereas X4, X5, X6 belongs to not A. So it's either A or not A. Okay, so right, like I said here, this is the solution we know because we made up the data before. But in real life, obviously we don't know this, and this is what we're trying to find. Like we want to find F, the optimal, and this F tells us the cluster. Like this 1, 2, 3 belongs to cluster 1, 4, 5, 6 belongs to cluster 0. Okay, so today, like with this kind of solution, as well as this type of relationship, like I said before, you can just randomly pick any solution or all combinations of solution one at a time and then calculate their relationship. And once you've done that, for every one of them, you pick the smallest one. But then you have to go through a lot of combinations, like 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0. And you don't want to do that. You don't want to have to go through every combination just so you can find the best one. So today, yeah, we're going to try to find the best one mathematically and in a better way. And to do this, we start with this. This is the objective function that we've been looking at. And the first thing I do is I take the square of this. I do that here. And after that, I take this and I multiply and distribute to all three of them. Okay? You can see, once I've done that, we have three portions. I call it A, B, C. Now, A and B, if you look, I mean A and C, if you look at it carefully, they're basically identical. Well, they are identical. looping through Fi is the same as looping through Fj, because j and I both increases the same way. So anyways, the reason why I want to divide them into multiple portions is because if we just look at one, it's a lot simpler to look at them one at a time. Anyways, so this is part A. And in part A, the first thing I do is I separate this out. So before it was Ij here, Ij, but I separate out so it's easier to read. So now we have two summations, I and j. And after that, I just look at this portion. What does that mean? It means that we're going to add up all the j's. Okay? So what that means is wi j is equal to 1, wi j is equal to 2, wi j is equal to 3, and we're just adding all of them up. Okay? That's what that means. Now, since fi is all the same, we can just pull this outside, which is right here. After we pull this outside, we look at this part. Well, I is the same. Notice I is the same, but j changes. So if you remember the adjacency matrix, W11, W12, W13, and go on, W21, W22, W23, so on and so forth. Now, when we add up the entire row, it has a very special name. It's called degree of vertex. Oops, degree of vertex. And when we add all these up, degree of vertex, we call it di for the ith row. So this right here is the degree of vertex, di. Okay, so we have simplified this whole entire portion. Next, well, what does the I mean? Now we need to add it all up. D1, F1, D2, F2, D3, F3. And I claim that this is the same as this right here, where the D is the degree matrix, and the F right here is the solution. If you remember, F right here is F1, F2, all the way to Fn. So is that really true? If you've never seen this before, you might not know this property. So why don't we test it out so that you can be convinced? Now, remember, let's try it with a very small one. Just two dimension, F1, F2, and then this is the degree matrix, D, and this is F transpose, okay? Now, if we just multiply this out, it's very easy to show. You see, we'll multiply the two of them. So it becomes F1, D1, F2, D2. Now we multiply the two of them together, and it will look like this. D1, F1, D2, F2, D3, F3, and etc., etc. Now, it's pretty easy to see that they are identical. You might want to pause the video and just like stare at them for a couple seconds, that they are indeed identical. And therefore, this right here is really the algebraic form, whereas this is the identical thing, but in the matrix form, matrix and vector, where F is a vector, D is a matrix, and F is another vector. So that's what it is. We have rewritten part A, okay? This is part A. We've rewritten part A from the algebraic form and rewritten it into the matrix form, which looks like this, okay? Now, let's look at part B. Part B starts like this. And I do the same thing where I divide ij into two separate sums. And then notice, first we look at this. Well, this is looping through all the j's. And therefore, this I here is a constant. And I just move it outside. You see, fi. And I combine these two together. So it's right here. Okay, so now I separate them out into the sum. Whereas Wi1, Wi2, Wi3, and all the way with F1, F2, F3. Now, this could be also vectorized where into this form. It's easier to see this. If we have A1, B1 plus A2, B2 is equal to A1, A2 times B1, B2. It's the same thing. Okay? So I am saying I'm using this relationship here on this right here. Okay? Well, what is this? Like I said, that's just F. And therefore, I just write F here. Okay, now we look at this part here. If we look at this part, you see that, well, this is F1, and then F2, and F3, etc., etc., etc. Now, at the end, F, that's all the same. So we can move that out again, like this, right here. This is F right here. And this part, now imagine this as A1, B1, A2, B2. We can now separate this thing, using the same relationship before, right? Over here. So this become F. So this right here times F1, just like that. This right here times F2, just like this. Okay? So far, so good. Now, what is this? What is this thing here? Well, let me rewrite this nicely. W11, W12, W13, W21, W22, W23, W31, and this just keeps going, right? Well, if you remember, this thing was the adjacency matrix, which we call it the big W. Adjacency matrix. Okay? So, and this right here is F transpose. Now, we did the same thing. We went from the algebraic form into the matrix form. Where here's the F vector, and here's the matrix. So, now we go back to the original relationship, okay? This is the original relationship we were looking at. Remember, A and C are the same. So I'm just going to say 2A here. I'll rewrite this and add the 2. And as well as for B, I'm just going to copy the relationship down. Now, once I've done that, I'm going to rewrite from the algebraic form into the matrix form, which we calculated like a second ago. Okay, now this F and this F is the same, so we can move it outside. This F transpose is also the same. We can move that outside. And this right here is the degree matrix minus the adjacency matrix. There's a special name for this, and it is called the Laplacian. We call it L. Laplacian L. So now we basically simplify this down to this, F times Laplacian times F. Of course, if you remember from previous video lectures, if we have a constant, right? If we have a constant and when we're trying to minimize something, the constant doesn't matter, right? Let's say we want to find the minimum x point, right? With this x equals to y. So the minimum point is x equals to 0, obviously. And it doesn't matter if you put a constant here. See the constant? Now it's 2x. The x is still 0 where the minimum is. So when you're looking at minimums, we can just neglect this. And now that further simplifies it, okay? We can remove the 2 at the front to further simplify into this expression. And from our previous video, you might remember how we find this f when we're trying to minimize it. If we're trying to maximize this whole expression, we will find the most dominant eigenvectors, or the most dominant eigenvector single. And that will give you the maximum. And if you had used the least dominant eigenvector or the smallest eigenvalue, eigenvectors, you will find the minimum. So that's all you do. Now you basically found a solution that you want. Of course, ideally, we want this solution. But if you had done find the eigenvectors, it's actually more like an approximation. You will see something that's more similar to this. Of course, you can still separate them out. Like, it's pretty obvious visually. So what you do is, once you have gotten this form, right, you with the eigenvectors, all you do is to run k-means on it. So if you run k-means, it will automatically, the k-means will automatically separate this and this out. Okay, so we start from here, run k-means, we get this. And here is our final solution, F. And that's how you get the clustering using spectral clustering. Now, it's very important to remember, with one eigenvector, it allows you to separate cluster A and not A. That was the idea. But if you have more than two clusters, then you need more eigenvectors. Let me explain with an example. Let's say that we have three clusters, okay? Alpha, beta, and gamma. And we therefore need three eigenvectors. The first eigenvector, first one, tells us whether something is A and not alpha, alpha and not alpha. And the second eigenvector will tell us beta and not beta. And the third one will tell us gamma and not gamma. So the original assumption was only binary, right? It's only binary. It's whether it belongs to inside group A or it doesn't belong to group A. And therefore, if you have more than two clusters, you need to start using more eigenvectors. So it's very simple. You just pick the smallest eigenvector, and then the second one and the third smallest eigenvector in this case. And then just make that into a matrix, and that is, you can use that as a solution. So now that you have this, all three of them, you still perform k-means as if each row is the new sample. Okay, each row is a new sample. And after you got the k-means, here's your final result. Like an example of this would be like three of them, right? Each row. Now each column is an eigenvector. And then you look at each row. And from here, if you observe this carefully, it's easy to see how k-means will divide this up. If you have k-means, you'll probably divide something like this, where this is one cluster, and that's another cluster. And this will be 1, 1, 1, 0, 0, 0. So that's it. That's the general idea of how spectral clustering work. It is really, really cool. It's currently probably the most powerful clustering technique out there. I mean, there are advanced versions of it, of spectral clustering, that like removes noise and does other things. So what we're looking at today, what we have looked at today is the not normalized spectral clustering, which provides the foundation of understanding spectral clustering. But most of the time, we actually in practice don't use the unnormalized spectral clustering. What we use is the normalized one. But you have to understand the unnormalized one in order to use the normalized spectral clustering. So I think in a future video, I will go over this technique, which requires you to understand the unnormalized version. And it's really just an add-on of like how to convert the data slightly. As long as you understand the unnormalized version, the normalized version should be very, very easy. So yeah, this is video 8. I guess I will see you in the next video.